And all right, so let's talk about the exam, right? Fortunately or unfortunately, I just posted the video from review session yesterday. We're going to run over another review a little bit in depth about the exam today. So I hope you can take some notes and we can get more information out of it. So before I do that, let me share my screen. Okay, so here to this. So the exam is going to be scheduled tomorrow. We're going to have a 1 hour exam content, but 3 hours for you guys to work on it. Okay, so it's like the previous format. All right. Now there are 4 problems. There's a irregular section, T-beam basically, and there are shear, and there are one-way slab, and there's serviceability. We're talking about moment inertia and crack moment inertia for the sections. Okay, so these are the problems. Now there won't be any multiple choice problem. All of the problems going to be like solution type of problems. So you have to write them down and solve the whole problems. Okay, and for the references, you're allowed to use notes. You're allowed to use the homeworks, whatever you have at hand. But I think you probably don't need all of those because the problems are quite different. Okay, so let's take a quick look what we have learned so far. All right, so I opened up all the notes that we have talked about before, and so let's just quite quickly go over them. So here's the shear on the sections, right? So we talk about how the shear stress is distributed in the beam and how we calculate the shear stress. And also we talk about what kind of shear failure we might have in terms of cracking, right? So we have a diagonal crack, we have a transisting crack. Okay, so now these are just the mechanism. Since we won't have any multiple choice problems, so these are not going to be tested. But mainly what we worry about is the concrete and stirrups, right? The concrete contribution and the stirrups contribution. So in terms of concrete contribution, there's a VC, and we need to know how do we compute VC, okay? So here's a simplified equation to compute VC. You really need to know how to do this. Okay? So figure out which parameter represent what and figure out the correct parameter to be used here, okay? And now why I mentioned here is that you might see a different cross sections of the beam. You might see a different cross section of the beams, so you have to be really careful. Okay, now this is just a concrete contribution, right? So what you do is you take the lambda, which is a coefficient accounting for the low lightweight or normal weight, and the compressive stress and prime C with BW and the depths, right? And you go on to do the simple things, right? And then for the stirrups, now we talk about it, right? The contribution for stirrups is basically the yield strength of steel, FYT, multiplied AV, which is the cross-section area of the stirrups legs. Now, usually we have two leg stirrups, okay? So don't get your area wrong. The other thing, for the shear resistance, the stirrups are mainly arranged in spacing. Okay? And then you have to use the the depth divided by spacing to give you the effective resistance from the stirrups, okay? So this equation, you need to remember this equation very well, okay? Now, there are inclined cases, where we have angles, we're not gonna test this in the exam, okay? All right. So now here we have it. We have the concrete contribution, we have the stirrups, and also we have to compute the strength reduction factor when we add them up together. For shear, it's always 0.75. For shear, it's always 0.75. Okay, so have to remember this equation. Okay, all right, so let's go to next lectures. I believe it's 13. We talk about this. All right, so like I said, for the stirrups, right? There are minimum requirements, and in terms of reinforcement, AV min, okay? In terms of reinforcement, AV min, and this has to be satisfied. So you need to know how to check it. And of course, this is just a minimum reinforcement. And once you have the minimum reinforcement provided, you can calculate the concrete contribution VC using the simplified approach, which remind you that 2 lambda squared root of prime C BWD. That's the concrete contribution. And from there, you can compute the shear resistance from the stirrups and then reversely calculate what's the required spacing for the stirrups. What's the required spacing for the stirrups? Okay, so the required spacing for the stirrups come from the provided steel area and also the applied shear. Okay, now in the shear design scenario, normally the bars are selected for you, right? So either number 3, number 5, number 4, and you are responsible to provide the spacing requirement. Okay, so that is for the shear. That is for the shear spacing. Okay, shear spacing. All right. So these are the requirements for the spacing, right? So when we have minimum requirement, the maximum spacing has to be half D, 24 inches, and if VS bigger than 4 square root of prime CF BWD, maximum spacing has to be less of a quarter of D or 12 inches, right? And this is two bit and pieces, right? So to put them all together, to put all things together, now we have 2 tables, right? So the left table and the right table. The left table is when the stirrups reinforcement contribution VS is smaller than or equal than 4 times square root of prime CBW, you use this table. And if it's VS bigger than 4 square root of prime CBWD, you use this table. Okay, now this is to calculate the spacing. So I just want to ask a quick question here. What if I gave you the stirrups and gave you the spacing, right? If I gave you the stirrups, I gave you the spacing, you need to know how to compute VS, isn't it? So if you look at this, VS is essentially equal to AV FYT multiplied D divided by S spacing, right? So if the stirrups is provided, and ask you to find out the resistance of the section in terms of a steel, you can find it. You need to know how to find it, okay? So you need to know how to go both ways. All right, so this is the concept for shear. And don't forget, the maximum shear resistance from the stirrups cannot exceed 8 times of square root F prime CBWD, okay? So this is very important. All right, okay. So once we have done that, we moved on and we talk about critical sections. And these are the critical sections, right? So most of the cases, we have simply supported conditions or cantilever conditions, right? It's either simply supported, which is this case right here, A, let me use red, okay? And if it's continuous supported, usually like a B, column beam joints or beam foundation joints. In either cases, right, the critical section is D, distance away from the edge of the support, right? From the edge of the support. Okay, so you need to know the location of critical section. You need to know the location of critical section. Why this is so important? Because if, for example, I have a cantilever beam like this, okay, if I have a cantilever beam like this, and say I apply a load, point load, all right? It can be here, it can be there, doesn't matter, right? Say I apply a point load here, and the shear diagram looks like what? Looks like just like this. This will be the shear diagram, right? Because it's constant shear, isn't it? So when you design for it, you need to find out the spacing, which, not the spacing, but the critical section, which is D, depths. Okay, these are the bars here. D, depth away from it. So this will be the crack, at, and this will be the location. Okay, so when you design for shear for this cantilever section, you use this section. Now, if it's cantilever beam, it is quite straightforward. There's no shear change along the length, along the span length. But if you have a simply supported case, right? If you have continuously bounded case, right? Or a simply supported case, either way, or simply supported case, right? And be careful on the shear, okay? Or you have a distributed load, what the shear diagram looks like, right? Save you the trouble, triangle. This is what it looks like. So for these cases, right? For these cases, need to find out the critical section like this, find out the critical section like this, and design for it. Design for it. Okay. So this is all you need to know for the loading for the critical section. Okay, for the critical section. Now we also talk about the design differences between ACI 14, ACI 19. Since we did not have the textbook yet on the 19, so we're not trying to test you on both codes, confuse you, okay? Now, only one big difference you should remember is that if you use 14, when you calculate VC, you have to use a different approach, right? So when you have AV smaller than AV mean, which means if you do not provide any stirrups at all, you calculate VC using this equation, which is different from 14, And we will try not to involve this case in the exam, okay? We'll try not to involve this case in the exam, okay? So I just want to make it clear here. All right, so that is as much as difference between 14 and 19, between 14 and 19, okay? So this is double reinforced sections. Don't worry, this is review from the previous exam, but this is shear, right? So here we showed you a simply supported case, and we show you the shear diagram. We ask you to calculate the maximum shear forces, right? And then we ask you to find out the critical locations. So this is a pretty long process, okay? And then we showed you how to compute the minimum, if the AV mean is provided, that means if the minimum shear reinforcement is provided, we ask you to compute the VC and ask you to compute the VS, right? And this is how we showed you before, okay? If you forgot about it, go back and review all these notes, okay? Now you see there are a lot of critical sections, And I mentioned that you might have to design it for different spacings. Okay? And in review, the exam problem, of course, hasn't been finalized yet. I would say that if we were to ask you guys to design for different sterile spacings, the number of regions, right, you have a different spacing will not exceed more than 2, okay? Will not exceed more than 2, or we simply do not ask you to provide any sterile design at all, okay? We simply will not ask you to provide any change of a sterile spacing at all along the sections, okay? So that is as much for shear, right? As much for shear. And I'm doing this very quick, okay? So I hope you're taking notes, or you go back later, watch my video, okay? So I think I missed some of the lectures. There are just lecture notes that I'm missing from my notebook. Okay, but let me talk about this. Yeah, this is serviceability. Let me talk about the one-way slab. Okay, so shear, I'm not so worried. Not so worried about it. Okay, I think you have find a lot of notes on shear, and the homework was pretty clear. Okay, I'm more worried about this one-way slab business. The one-way slab business. I think when we went over it, it was pretty fast. A lot of details might got missed. So we have to be careful on this, okay? So on the one-way slab, right? On the one-way slab, we actually talk about there are 2 types of reinforcement. One is a flexure reinforcement, and the other is a temperature shrinkage reinforcement. Okay? Now we talk about 2 things for one-way slab. One is the section design, which means we design it by strip. And the other is we find out the moment distribution of the structure. Okay, so in review, I want us to take a look at the backwards. So let's take a look at the structure first, right? Okay, now when we say flexure reinforcement, that means the bending direction is along, so use different color, okay, use blue for bending. So the bending direction is along one direction, okay? And you notice that some of your homework, you're grading, you might have lost some points in the one-way slab homework. I will talk to grader and correct some of the answer to that. But like I mentioned this again, there's only one direction for bending, okay? This is the direction for bending. All right, so I draw it here as a continuous one-way slab, as you can see from the right-hand side, okay? This is the bending direction. Okay? If this is the bending direction, when we do the moment coefficient, we're looking at the cross-section, which is the blue shaded area right now, okay? And find out the moment here, here in the middle span as well, at the support as well, here. At these locations, these are where I find my bending moments at. These are where I find my bending moments at. Okay, so don't get yourself confused. All these bending moments we're talking about, if I want to use double arrow, right? So they are double arrow in this way. Okay, double arrow means you put your thumb along this direction and rotate your 4 fingers. It goes this way, right? This is the bending moment direction, all the way across, all the way across. Okay, so when we design the section, we're talking about this cross section. Okay, when we design the cross section for reinforcement, we're talking about this direction. Okay, and this is the 12 inches of strip. This is the 12 inches of strip. All right, so essentially what we're doing is we're designing this slab, okay? Designing this slab in one-way direction along this direction, okay? So don't get yourself confused. Don't get yourself confused, okay? Now we talk about the moment influence line, right? Basically is we have a method of determine what's the moment at each different locations, right? But we said that's too complicated. So we are going to use ACI, moment coefficient, to do it. That means ACI gave us a table to do it, okay? And how we're gonna use the table is that we have to satisfy the criterions. So these are the criteria you have to satisfy. First of all, it has to be more than 2 spans, right? And second of all, the adjacent span length difference has to be within 20%, within 20%. Okay, it has to be uniform loading. Uniform loading means no concentrated loading. Okay, and additionally, the live load over dead load ratio has to be less than 3. Okay, and it has to be prismatic members. Means the square, right? Cannot be round. Cannot be irregular sections. Okay, and the last but not least is that the 1.2 dead load has to be bigger than the 1.4 dead load. Means if I do a 1.2 dead plus 1.6 live, come up with a number. And if I do a 1.4 dead, come up with a number. I have to make sure this is bigger than the 1.4, okay? This has to stand. All right, you will have to remember all these 5 criterions, okay? So do check them all before you start going into using moment coefficient, because if any one of these violates, you will not be able to use the moment coefficient and you'll be tested in the exam for this, okay? All right, so now let's come back to the problem, right? I already said one-way slide, only one direction need to be considered. So this is the direction need to be considered. And I took a cross section of that, this cross section on the side, right? This transverse cross section, and this is what you're seeing here. So in the exam, if you see a slab direction, if you see a transverse section like this, that means you're looking at a transverse cross section, okay? The bending direction is always this way. Don't confuse yourself, okay? It's always this way. All right, now, here comes the most challenging part, is determining the moment coefficient. These numbers, right? These numbers. Now, we have uploaded a table for it. Okay? So I think it's either 17 or 16, we have a table for it. And let me see if I have it here. But if you don't have it, that's okay. You can simply use these numbers in the notes, But when you use these numbers and notes, right, 2 things has to be considered. One, of course, these has to be satisfied. Right? So make sure this is check mark. All this has to be checked. Second, that these coefficients are applied because the end support is spandrel. What I mean by spandrel is that these are integrated together. If they're not integrated together, you cannot use this coefficient. So most likely you will not see a very strange case, but do check them, all right? Don't just jump in right in and start writing numbers. Make sure they are integrally built. That means monolithically casted, this is the beam and this is slab, they cast together, cast in place, okay? This has to be respected before you start applying moment coefficients. Okay, so that's how we get these numbers. Like I said, if you have the table, use the table. If you don't, use these numbers are fine, okay? Use this number fine. The second critical point is the span length, Now, watch it. When we say span, when we say LN, these are clear span. That means from edge to edge. It's not from center to center, it's from edge to edge, okay? So if the problem gives you from center to center, you need to subtract the thickness of the beam to get the clear span, okay, to get the clear span first. Now, if the problem tells you it's clear span, then you're in luck. You don't have to do that, right? So first thing first, find the span length, right? So once you find span length, you run a check, right? You run a check. And we will most likely give you the dead load and live load. And people still asking question, look, Bob, if you say the self-weight has to consider, what do you mean by self-weight has to be considered? Like I said, right, you just use the height, which is HF, right? 6 inches multiply 150 pounds per cubic foot. And that give you the self-weight of the slab, give you the self-weight of the slab. If we say the beam has to be considered, instead of 6 inches, you add the beam height as well. For example, I don't know, this is 22. So use 22 multiplied by 150 pounds per cubic foot. Okay, so just use different height to multiply the density, you get the self-weight. You consider the self-weight. All right, so that's how you consider the dead load. Now, pay attention, right? Folks, when we say the live load and dead load, right? These are live load and dead load are distributed like this. They're distributed like this, okay, in this direction, along this direction, okay? So you have to find omega u. You have to find omega u, right? So omega u simply is omega u equal to 1.2 dead plus 1.6 live, okay? And when you run the checks on the right-hand side, you know that whether this dominates or not. If this does not dominate, I mean, if the 1.4 dominant, then stop doing it. You have a problem, right? You have a problem. So make sure you can use that. Once you have omega u, once you have a clear span, you can use this coefficient to calculate the moment. Like I keep saying again, for instance, MUA is the moment at support A, and that is minus 1/24 omega u Ln1 squared, Ln1 squared, which is clear span squared, okay? Since it's negative, so negative moment here. And in the middle span, there's a positive 1/14, there's a positive moment here. And at the end B on the left is minus 10, on the right is minus 1/11, but 1/-10 dominates, so we use 1/-10, okay? We use 1/-10, whichever one is bigger at the support, okay? So don't confuse yourself, right? So now, there's no problem if you're at the end of it or in the middle span of it because you only have one span length. Now you might have a question is that if you are at the junction here, on the left and right have two span lengths, what you do, right? So this is what you do. You use the average. You use the average. Okay, in the exam, we probably draw you a section we ask might be here, I don't know. We're just gonna pinpoint some of the points you have to find the moment coefficient, find the moment and design for it. Okay, find the moment and design for it. All right, so here, these are the moment and you just compute that, right? You have all this loading and you find the span length and compute that. Now, last but not least, when you calculate, make sure that you do have the unit correct. They are kept foot per foot. For one-way slab, everything is per foot. Everything is per foot. So make sure you have a correct unit. Make sure you have a correct unit. Okay. All right. So this is structure part. Right? That means once you know how to distribute the moments, right? So from the whole thing, all you got is MU. Okay. All you have from this whole analysis, right? The whole analysis gives you MU. Right? Now, how to design for it? We take this MU and we take a look at the cross section as 1 foot, a 12-inch strip, and we will determine what is the reinforcement at the bottom here. What is the reinforcement at the bottom here? So that is our issue. That is our issue. Okay. So let me stop sharing here and share my screen on how we design a cross section. All right. How we design a cross section. Okay. So can you guys see my screen, guys? Can you guys see it? All right, so that's silent. I assume you see it. Okay. Now, again, like I said, with all the calculation we've shown so far, we essentially find moment for this cross section. And this cross section has a 1 foot of width of strip and height of HF. That's the section we're designing for, okay? And the bottom bars are the flexure bars we're taking care of, okay? For the flexure reinforcement, right, I want to emphasize again, it's AS per foot. That means if you were given the bar, a single bar, you calculate the area for a single bar and convert that by 12-inch, which is the foot, the length of the section divided by the spacing, okay? Divided by spacing, and you get the AS per foot. That is required reinforcement ratio, okay? That is the requirement reinforcement ratio, okay? So vice versa, you can reverse this. you can reverse this. If you were given the bar size, AB is given, right? If AB is given, okay? And you can calculate the spacing given the required reinforcement, okay? Now, don't forget, the maximum spacing has to be smaller than 3 times HF or 18 inches per ACI, okay? These are additional requirements, all right? Additional requirements. Now, these are additional requirements for cracking, and previously, these are the additional requirements for deflection, okay? So I have to make sure all this. So these are the spacing for requirements for the flexure, okay? Now, we also talk about shrinkage. These are the shrinkage requirement. AG is the gross section area, okay? Gross section area, all right? So AG is BHF, don't forget, the B is the 12-inch strip length, okay? So here, another drawing just to emphasize the one-way slab. So this direction along my mouse direction is the bending direction. The other is the temperature shrinkage, don't forget, okay? Don't forget. All right, so I even cut out the cross section, right? You can take a look at it. And these are the shrinkage direction, and the long bars, the dots are the shrinkage reinforcement. Long ones are the flexion reinforcement, okay? Long ones are flexion reinforcement. We run you an example how you design it, okay? So imagine this. This is basically one bay of the cross section we showed previously in transverse sections, right? To find the moment coefficient. This is just one bay of it, okay? So you were given all this, trying to design for it, right? So if you already have MU, you don't even have to worry about the load distribution, right? You just start from here. You don't even have to write omega UL1 squared divided by 8. You don't have to write all this you don't have to worry about. You already have MU from previously cross section, right? From moment coefficient. So you use this MU, right? Bring in here and pursue the calculation, the reinforcement using this equation here. Okay, so you go on and find out the reinforcement, so on and so forth, right? You find that AS is this, and this is the required reinforcement. Now in the slab, we will tell you what size of bar you select. We'll tell you what size of bar we select, okay? Now, if we tell you the bar already, right? Don't use any bars but the bars we give you, right? And convert that and find out what is the spacing, okay? So I want to emphasize this again. For one-way slab, it is the spacing we're designing, not the bars. It is the spacing we're designing, not the bars. So the final answer for one-way slab design is the spacing, okay? Is the spacing, right? So review this and make sure you know how to do this, and that is what we're asking for, okay? For one-way slab design, All right, so let me close this up and continue on. Probably let me go back to my notes, okay? Let me go back to my notes. Give me 1 second, switch. All right, okay. All right, so that's one-way slab. Okay? So we talk about shear, we talk about one-way slab, okay? And we haven't talked about T-beam. Okay? So let me see if I have the T-beam here. Well, let me save the T-beam at the end. Let's talk about deflection first, because I easily forgot the deflection, okay? So there are two things in deflection we are going to test you on, right? It's basically gonna be the moment inertia, The deflection calculation equation we mentioned on Monday, that's not part of this exam, okay? Let me say this again, that's not part of this exam. Probably have it in the next exam, but not right now, okay? So for the moment inertia, when we talk about moment inertia, there are two. First is called transformed moment inertia, and that is on the uncracked stage. And there's a cracked stage, we'll talk about cracked moment of inertia, So first of all, in the uncracked stage, how do we compute that? You need to transform the reinforcement. And this is the part you transform it, use n-1 AS, transform it. You have the steel in the longitudinal direction, and then you can calculate the moment inertia using this table here. Okay? This is quite essential. You have to know how to do this. Okay? You'll see a problem like this. Okay? What if, you may ask, what if I have a T-beam? You do the same thing, but in addition to this, you can make it more, component. Okay? Since it's a T, you can take the flange as part 1, take the web as part 2, and take the reinforcement part 3 and pursue this computation, right? It's the same thing. Okay. All right. So that is for uncracked. For cracked, right? For cracked, you use this equation. You use this equation, right? KD, they tell you the compressive zone size, you compute it, and you're fine. In using this equation, right? Take a look at this equation. N is a modulus ratio, okay? AS is a tensile reinforcement ratio, sorry, tensile reinforcement area, okay? Now, some of you may ask the question, what if I have a T-beam, right? And what if my KD exceed this, right? Well, the answer to this question is that mostly we're gonna maintain it here within the flange. Now, if so much that the KD exceeds this, you cannot use this equation anymore. You cannot use this equation anymore. So what to use? I have uploaded a file. I have uploaded a file on Canvas, show you how to do that. Show you how to do that, okay? So let me show you my screen, okay? Let me show you my screen. Where are we at here? Okay. Okay. So this is how we do it when we have a compressive reinforcement. Have a compressive reinforcement, right? So if you have a T-beam, if you have a T-beam, simply switch the top compressive zone with whatever you have there, okay? And redo this center thing, right? Trying to find center first, right? And then pursue the following computation, proceed the following computation, okay? I'm just gonna briefly say here, okay? In the T-beam, normally you can use the KD equation, okay? We're not going to make it very complicated for you, okay? So don't have to worry about it. But I want you to review this just in case, okay? I want you to review this just in case. All right, so let me stop sharing this and let me try to find the T-beam section. T-beam section, I believe it's either in 21, 22. Give me 1 second. Okay, 23 is, okay, 22 is a one-way slab, okay. All right, there's some software issues. I cannot open this. Okay, hold on 1 second. I think I have it in one-way slab examples. This is one-way slab. All right. Yeah, I think some software issue this morning. Canvas is now helping me out, but let me see if I can open up here. Yeah, slowly. Okay, let me open up here. Okay, stop sharing. All right, so this is additional example one-way slab. It's in the file folder and there's a one-way slab example. Okay, so let me show you where it is. You can go here, there's a one-way slab example. There's a note April 14th, 17th, that's from last semester. This additional example, I just wanna show you, okay? So as you can see, this is one-way slab direction, okay? And you see the cross sections. This is additional example, how we calculate it. And that's the same. Yeah, that's the same cross section we're taking a look at, okay? So this might be something similar in the exam, all right? Just take a quick look at this one, okay? And now, in addition, I posted the textbook one-way slab solutions, okay? So you can take a look at the solutions. The one thing I just want to point out when you take a look at it, now this MU here, they just use the coefficient, right? They use the coefficient. They did not assume simply supported conditions, right? So we'll do the same thing. We'll show you the structure, compute MU and go from there, okay? Compute MU and go from there. All right, so last but not least, okay? So let me find my T-beam. Let me find my T-beam sections, okay? So here, yes, I think so. All right, let me give me 1 second, share this. Okay, T-beam. T-beam was taught right after the first exam, before the second exam, okay, before we got into it. So I just want to take a quick look. Now, these are the T-beam. So we have a flange, we have the height, and we have the reinforcement at the bottom, okay? And we talk about how to divide the flange into the wing part and the web part, and ask you to check if the compressive zone is within the flange or exceeding the flange in the web, okay? So you need to understand which way it is. Okay, you need to understand which way it is. So this, I believe, is in the lecture 9. It's in the lecture 9. So make sure you have it. Make sure you have it, okay? So don't forget, okay? Take a look at it, okay? Now, in most cases, the compressive zone usually, most cases usually is in the flange, But sometimes the compressive zone is outside the flange, right? So in the exam, since the time is limited, I cannot say for sure which way is going to lean towards. But if you have the compressive zone outside the flange width, make sure you did it right, okay? Make sure you did it right. It's very strange that your compressive zone outside the flange, okay? All right, so this is that for the T-beam. Now, one thing I just want to add here. So you see this as a T, right? You see this as a T-beam, okay? Nice and easy and this T-beam. What if instead in the middle of it, right, from the homework, you remember we have an end section like this, okay? So if you have end section like this, right, what you gonna do? Right? So if you gonna have a end section like this, instead of T, you can design it as an L, right? But same approach stands. First of all, you have to check if your compressive zone is within the flange. You have to check if your compressive zone is within the flange or not. Okay, make sure is in the flange or not. How to do that? Simple, right? Assume that the compressive zone is within the flange first and go at it and see if it's within the flange. Okay, see if it's in the flange. All right, so review this. Make sure you review this, okay? Make sure you review this, how we design for it, okay? All right, okay, ladies and gentlemen, I think that's all that you're gonna see in the exam. I picked most of the key points. If you understand all these key points, I'm pretty sure you're gonna do well. And if you haven't reviewed enough, some of the information I just went over seems a bit strange to you, you need a review, okay? You need a review. All right, so I'm gonna stop right here and welcome any questions. Folks, any question to me? Anything? All quiet? All right, let me do this. Since some of you may have questions, some of you may not. I'm going to stop recording. Then whoever have a question, welcome to stay behind. We can discuss. If you don't have any questions, I see you tomorrow, okay? And see you tomorrow, right? And I'll send the email tomorrow, remind you when the exam is going to start and how we're going to collect them tonight. Actually, I'll send the email tonight, okay? All right.